I'm Varun. I'm the PhD student at Surfax, and today I would be presenting the work on numerical study of thermoacoustic instabilities in spray flames. So, under the broad Magister umbrella, what was done at Surfax was mainly to improve spray flame modeling techniques, and that was applied on a realistic combustor configuration, which was chosen, which is the LOTAR, which I'll come to later. And in that, we have been able to analyze complex patterns, spray flame structures, which was sort of a first thing because it's a very big configuration, and also look at how to compute FTFs with the limited set of data we have and extend that to more complex fuel representations. So first thing was to improve the spray flame modeling. And in that case, what we wanted to do was move beyond what is being done currently in CFD simulations by considering a single component representation of the fuel. So what happens in general is we have hundreds of components, multiple different families of hydrocarbons, and each of them comes with its own evaporation behavior, gas phase chemistry, liquid properties that are changing over time. And also this is going to affect the overall flame structure, the regimes of combustion, and we want to investigate how that would look, how that would go on to the flame response as well. So to implement this kind of evaporation modeling, what we thought was to consider the discrete multi-component model. And what you do there is you track a few species. In our case, it has been 3 for the 2 fuels that we use. And in general, it's about 5 to 6, and you track them through the lifetime of the droplets. And it's a very good option because you can easily integrate it with the chemistry that is available, or rather the analytically reduced chemistry. So an example of that for Jet A would consist of 3 components, that is endodecane, methyl cyclohexane, and xylene. And we validated this with experimental results. And what you will observe is because of the high volatility of methyl cyclohexane, there'll be a staged evaporation behavior, and you will have the cyclohexane evaporating first, and then later on you have endodecane. So these kind of models were combined with chemistry. So what you do here is you have 3 different sets of fuels, and they are completely different hydrocarbon families. So how do you do that? You have a detailed mechanism of 230 species, which is probably too stiff and too large to run on a realistic case. So this part of the work was done on another project with whom I coordinate. So there are standard reduction techniques, and we end up with something that is more manageable, but you still retain the original properties of propagation speed, thickness, and heat release mechanisms. So the first step, what we looked at was to combine these 2 things. We started off with 1D spray flame simulations where we tried to stabilize a 2-phase flame and look at how the interactions between the 2 phases take place and studies flame structures. So video is going on over there. So this was actually done over a range of cases, for both rich and lean, different droplet diameters. Also look at effects which you observe in gas turbines where you have regions where the 2 phases are not together, are not at the same velocity. I will move on and not show too much of the spray structures, but this led to this development of laminar 2-phase flame speed correlations. And that was done considering the timescales for evaporation of each species, where you actually observe these multi-component effects that can be used, like the varying evaporation flux. So as I said, initially you have cyclohexane, and in the end you only have the heavy component evaporating, and also take into account the drag effects over the flame region for the droplets. And finally, you can compare the evaporation zone, the flame reaction zones, and come up with effective equivalence ratios, and also consider the fact that each of these components have varying contributions to the equivalence ratio. So with that, we could sort of match what is going on experimentally in terms of the numerical simulations. The one on the left is for a lean case, which is a very classical result. But the one on the right is interesting because you have a lot of models which just look at the overall equivalence ratio and predict flame speeds. But if you have the right diameter, even a rich mixture can propagate much faster than what you will actually observe. So this was the set of things that was done initially on 1D domains. And then we thought it was time to move on to something much more complex. And in that, what we want to see is there are a lot of complex spray structures over there. There are a lot of modeling challenges that are involved in a realistic combustor. And that is because when you inject, you have varied droplet sizes, velocities, liquid loadings, composition. And to test all those things, we have this configuration of the LOTAR test bench at Onera. And this was specifically designed to study thermoacoustic instabilities. And for spray flames, you have a complex injector system, a movable tube based on which you are varying the overall stability map. And the part that is being modeled is shown in the yellow part, which is the mesh obtained for the geometry. That's around 0.5 meter. And you have on the bottom part, what is on the left is the chamber, and what is tightened back is the plenum part. And both of them are separated by this complex swirler geometry. And there you have 3 swirlers, one radial swirler through which majority of the air is passing, and then you have 2 coaxial swirlers to break up the pilot jet. You also have multi-point injection in the radial swirler. So, and you have these complex or these cooling holes that are done to cool the imaging windows. So, this was the whole setup that we are trying to simulate. And why this is interesting is when you look at the power rating, the range of Stokes number over which the droplets are existing, the density ratio, and also the Reynolds number, you see that is much more complex than what is reported in literature at this point of time for spray flames. And the simulations we do are in AVBP. We have a 32 million mesh element, and there were 2 conditions. One was the cold flow case, where you have 100 gram per second of air, which was mainly used to validate the whole setup. The reactive cases was done at 450 Kelvin, and you have 4.55 grams of fuel. And this fuel, as I said, could be split between the multi-point injection and the pilot injector. But since this was the setup that was used to calculate the FTFs, they found a stable operating point over which to force when you have pilot-only injection. So that is the fuel split parameter. And then the injection itself was one of the topics to study, but the data is very hard to come by. So we use the standard models for injecting a hollow cone liquid spray over using a distribution, a standard Rosen-Ramler distribution. And these simulations were done for 3 fuels. The first was a single component kerosene representation with 2-step chemistry that forms the basis from which we can move on to more complex fuel representation. One is a 3-component mixture representing jet A, very similar to what I showed for the 1D flames. And another is an alternative jet fuel, which is sort of a synthetic fuel that is being discussed instead of jet A. So the compositions shown here and the contour plot show ternary. The contour plot is actually a ternary plot of the 3 components, where every point inside represents a possible fuel space. So for jet A, you have a very large arc at this point of time, 36 species, 543 reactions. That is because you have much larger detailed chemistry from which you have to reduce, and that is because of 3 different classes of components. And that is why there are some regions where the arc is not valid. For example, where you have extremely high composition of xylene in the mixture, it is very hard to get a flame at around 450 Kelvin. On the other hand, you have the jet B1 or alternative jet fuel, and you have there mainly branched hydrocarbons. So you have a smaller starting point and you end up with a very manageable set of chemistry that is valid over a large range, and you have minimal variation in flame speeds also. So I'll just show you the average profiles for these things. So as soon as you introduce this fuel, you see that there is some kind of change happening. So on the left, you have the monocomponent representation. The middle one, jet A, should ideally reproduce that. but because of staged evaporation, you see that the flame zone starts to extend. And in case of the alternative jet fuel, you have these regions of negative heat release that you can see where pyrolysis is taking place. But this does not give a complete idea as to what is happening. You see that when you look at instantaneous snapshots of heat release, you have several spots of heat release in the recirculation zone. And these are the regions where you have small droplets in high temperatures that are evaporating very quickly, releasing vapor, and then that undergoes quick pyrolysis, and then there is heat release. So there is a lot of work when you also look at the flame index, which would represent what is the regime that it is going on in. You see that the main flame front is more or less premixed, but the spotty things inside, sometimes you see it as a premixed flame, sometimes as a diffusion flame. But ideally what you need, and the other research question that it opens up, is we need some kind of models to handle these events where you have this single component, single droplets that are burning very quickly in these hot regions. But when you move on to an alternative jet fuel, the same setup, you see this initial flame base, which is dominated by the volatile components. You have a discernible pyrolysis zone followed by a main flame zone. And then when you look at the flame index, this pyrolysis region where you have an accumulation of all these smaller components actually burns in a very weak diffusion flame front with the incoming air from the radial swirler initially, and then that is followed by a major premixed flame zone. So you have a much cleaner representation here, also because of the chemistry and the thickness. So from this, the next step, we take one step back and look at the forced cases for the two-step kerosene. The frequency range over which they did the experiments was very small, that is 170 hertz, 212 hertz, and also for a range of amplitudes from 1.5 to 45. And on the left, you see the experimental data that they have given, and it's almost a flat response with very low gain. And we tried to see what would happen when we tried to compute the point where they have 30% of the inlet velocity as the forcing amplitude. So there was a lot of work done, and it's still being done. Even people at TUM are trying to do this forcing, but on a different configuration, the Sika configuration. Sometimes the flame does not respond when you force from the inlet, and you are forced to move towards outlet forcing. And then you have to also look at places where the flame is not well resolved. And a lot of work went into trying to get the right strategy to force such spray flames. And with all that on the right, you can see we have almost an agreeable match. And because of the low gains, it becomes very difficult to match both the gain and the time delay. And this is the best we could over this short experimental range. Just to look at how the flame dynamics is taking place, the one on the left, the video on the left, is the heat release variation for 170 hertz, and the one on the right
Has Varun frozen for everybody?
Yep.
Yeah.
Yes.
Yes.
Yeah. I think that's the bandwidth
for
of the
200 hertz, and it's more or less the same mechanic.
Maybe he's asking to switch off his camera.
Yeah. I don't think he can hear us either.
Flame.
Can you hear us, Varun?
Yeah, I can. Is there a problem?
Yeah, we lost you for a few seconds. You froze. Could you maybe switch off your camera, please? And maybe go to the previous slide and recap.
Yeah, just a second. I don't know.
It's too much information, too many movies. It didn't work.
It's not working. Okay. 1 second. Let me try to figure this out. Because my flame is, sorry, my screen is flashing all the time. So from here, yeah. So the first cases, as I said, was done over a very narrow range. And the problem is that because of the low gains, it was hard to match both the amplitudes and the time delays. So we have done whatever possible to get an agreeable match. And this is still a work in progress with regards to what's the best strategy to look at the force flame dynamics. But when you look at what is happening on the left and the right, because of the narrow experimental range, you see that it's almost a similar flapping response. And you have these events of separation of the tip of the flame just above the radial swirler. And this is happening at different points in time for this narrow frequency range. And what we're doing now is to extend it to almost 500 hertz, which would give us a better idea of the whole flame response with respect to the forcing frequency. And also, when you look at how this is going on, you have a point where you have extremely low velocity and low mass flow rate through the radial swirlers. And this is when the droplets get trapped in the hot gases, and you have an increasing evaporation rate that leads to a very high equivalence ratio. And when there is a lot of fuel that is ready to burn in that region, and you have again an increase in the mass flow rate through the radial swirler, is when you have this event of almost separation. It almost detaches the part of the flame at the top, and then you have an increasing heat release. So the next step with this as the basis was to move on to forcing the more complex case. So this is the case with this alternative jet fuel that we are trying to do. And you see a complete nonlinear response here, where you have these events of pyrolysis that are followed by extreme heat release rates. And this is how the signal looks for a couple of cycles at this point of time. We want to see why these events happen, where you have an initial heat release that is followed by a peak. And this would be an interesting thing to look at. And that is the reason we want to move to a much higher frequency, because it's easier to compare.
Varun, we're not seeing anything right now. No movies, no slide moving, at least from my side.
1 second. I don't know what's happening. Can you see my screen still?
Well, it's still
No,
the slide 17. The two
slide 17.
Slides. Okay. 1 second.
Maybe you can stop sharing the screen and start again.
Yeah. Let me try. Okay. This has never happened to me so far.
Well, there's a first time for everything.
Yeah.
Can you see it now?
Yeah.
Screen?
Yes, we see the
maybe to
PowerPoint,
skip
but
Yes,
not yet in
maybe.
presentation.
Okay, I won't go into presentation mode probably. So this slide 17 was this flame response that I was trying to show. I hope the video is running now.
Yeah.
It is.
It is, okay. So on the left was what was happening for about 170 hertz. And on the right was the end of the frequency, experimental frequency zone at 212 hertz. And because it was a narrow range, we don't see much of a difference in terms of response. Okay, so this was the main difference we observed. So this is this visible? The separation at the point at which the flame separation happens. So we wanted to look at why these events are going on. And that is why we looked at the mechanisms. So what we figured out was at around a phase of 108, you have a low velocity or a low mass flux through the radial swirler, because of which you have droplets that are getting trapped and evaporating, leading to an increase in equivalence ratio. So we have all this fresh fuel that is sitting. And when you have, again, an increase in mass flux through the radial swirlers is when you have this separation event and increase in heat release happening. And from this, we are trying to force this complex jet A fuel. And in that, I hope this video plays now. So yeah, we are observing these nonlinear effects where you have this initial increase in heat release, then followed by a second staged increase in heat release. And this would be why we want to move to higher frequencies, so that for this complex set of these simulations are very heavy, so a higher frequency would give us enough cycles to average and look at what is happening to find out the difference between different fuel compositions and a single component representation. Is this visible to everyone, this video?
Yes.
Okay, so let me just, so that was the last slide. So with that, I wanted to show that the work done at Surfax was in line with what was initially proposed with respect to improving spray flame modeling capabilities and then applying it to a larger combustor configuration. And then we were able to extract FTFs, and from those FTFs, I think for the small range, we can also look at putting them in the AVSP code and looking at the modes and the changes in the fundamental modes of the system because of these evaporation effects. And then we want to extend these FTFs to a much higher frequency range and also look at the differences between the various cases with respect to multi-component fuels and the effect of different staged evaporation on the flame response. So the part I showed with respect to the flame structures will be presented to the ECM meeting next month. So I'll probably send over a draft so that everyone can look at it. And in terms of collaboration, so I've been very lucky to work with the Annulite ESRs at Surfax. There was another jet screen project with respect to the chemistry where there was a lot of interaction, and with Sagar at TUM for the Wiener-Hoff inversion, the AVBP simulations, and also at Safran Tech for this LOTAR configuration, which was also another secondment. So I don't know if the videos work. Probably I could show you in the end again, but if you have any questions, then I would take them.
Okay, thank you, Varun.